Okay, so as you perhaps know, a very important property of our wave equation is that the solution is very smooth. And that is a very important property to know, especially when you want to improve the accuracy of your solution. And that will be, especially then, the summer semester, a course which will base on this course here, where we will also discuss of so-called finite elements of higher order. So you do not decrease the mesh size, so you do not make the mesh finer and finer, you just let the mesh as this is, but you increase the order of the basis function, which makes no sense when you have any singularities. If you have a re-entered corner, for example, in structural mechanics, then you should refine the mesh and not increase the order of the basis function. Anyway, we have now the wave equation, and the wave equation has this special feature. So in order to know about time and space discretization, the most important quantity is the frequency we have, and it is the frequency of our excitation signal. So the right-hand side of our partial differential equation, how the acoustic waves are generated. When you think for a loudspeaker, it is the audio signal you put on the voice coil, and the audio signal has some spectrum, and there we will see the important frequency is always the highest frequency within the excitation. So the rule of thumb is that in a space discretization approach, we have to resolve the wavelengths. Yeah, and it is very similar as you do a Fourier transformation in space. We have to resolve our periodicity in space, which is the wavelengths, and a good rule of thumb is 10 to 20 linear finite elements. It is going more towards 10 finite elements when you do a harmonic analysis. When you do a transient analysis and you have very fast changes in the excitation, meaning high frequencies, then perhaps it makes sense to go towards 20 linear finite elements per wavelengths, and clearly we will see we will have to resolve the smallest wavelengths, which is defined by the largest frequency. Well, more or less the same we have for the time discretization. So we know the period is 1 over frequency. We want to sample the period with 10 to 20 time steps, and we know the period is the smallest for the highest frequency. So again, for the time discretization, the highest frequency of the excitation signal is of most importance. Yeah, and then what is also a very important advice is to have very less distorted elements within your computational mesh. The best is when you have rectangular or hexahedral elements in 3D, not really strongly deformed quadrilaterals, for example, or TEDs. The best is really to have, let's say, even in 3D, really brick elements, so the side lengths are the same. Our fundamental equation, as we already know, is also the fundamental equation we need for the discretization, and this is this relation. We know that the wavelength is the speed of sound over frequency. Now the speed of sound, for example, for air, as you know, is about 340 meters per second. So this is a property of the medium where the waves are propagating, and we can assume it as a constant value for linear acoustics. And so you see the most important quantity we have here is the frequency, and the largest frequency, so the highest frequency, will give us the smallest wavelengths. And then with this smallest wavelengths, so let's write it here as lambda min will be C over F max, and the smallest wavelengths is our most important quantity. And there, as already discussed, we should have about 10 to 20 linear finite elements per wavelength. If you have quadratic elements, so the basis functions of your approximations are second order, then you can divide this by at least 2, so it would be 5 to 10 elements. Okay, let's look at a simple example. It is actually a 1D example because we have, as you can see here, a propagation along a channel. We excite on the left-hand side with such a pressure pulse, and we are looking how this pressure pulse is propagating through the channel. Since we use here on the upper and lower side homogeneous Neumann boundary condition, it will be just a plane wave. We also excite at the full length of the left-hand side, so just plane wave will propagate along this channel. You see, we will have a monitoring point in the middle of the channel, a distance of 2 times lambda. Clearly, the question is, what is the wavelength? We define here the wavelengths that we take here, this as the period, and then we can compute out by 1 over this period the frequency. As you know, when you would do a Fourier transform of this signal, it is like the Fourier transform of an infinite long sine function, which has just one value at the according frequency in the spectrum. However, due to this windowing, and it is like a kind of a, I just put it like here, rectangular window. It is, as you know, then a convolution of the Fourier transform of this rectangular window with the Fourier transform of the infinite long sine, and which makes then your spectrum broader. So you will also have incorporated higher frequency as just this main frequency, which we compute out as just discussed. Okay, so what we have done here and we are investigating is, okay, we take, as you can see here, we take here this rule with 20 linear finite elements per main wavelength, and we have also here the time discretization by 1 over 20 f main. So perhaps I write down, so if this here is, let's call this T main, then F main is 1 over T main, and our lambda main is this C, speed of sound. So let's C over F main. Okay, in addition, we also investigate a second discretization. So you see, we make here a finer time discretization, then space discretization, and then we make the same discretization rule with 60 linear finite elements per main wavelengths and 60 samples, time samples per main period. The result is perhaps not as promising as we would have expected if you are looking here. Actually, when you have this as an excitation and we have a plane wave traveling, we have no damping, nothing. So you should also record at the monitoring point the same signal as the excitation signal without any deformation, without any additional ripples, as you can see, and with a constant amplitude. So a maximum was here of 1 Pascal and minus 1 Pascal. So what you see here is that we get it quite nice already with the finest discretization, but this was already a factor of 60. That's the red one. If you do the standard rule, you see the blue one, which is not as nice as you can see, but this is clearly due to this extreme excitation where you cut off the excitation immediately after the first period. And if you think it from a technical point of view, you have any power amplifier, then it would be very difficult to immediately switch on and switch off. You always have some slope. Okay, a second important thing is here standing waves. If you have such investigations where you have standing waves, then you will see you need also a more fine discretization in space and time to get good results. And it is the following. What we have here is, this is the axis of rotation. We have here, let's say, a disk, and this disk is just vibrating at a fixed frequency, and the waves are propagating. You have here an obstacle, so you have reflections. And in order to model free radiation, we have here this perfectly matched layer, which is just absorbing the waves and which models an infinite propagation domain. Clearly, due to these obstacles, we have waves traveling forth and back, and after some time you get the steady state solution, which we immediately get when we do a harmonic computation. And this is, as shown here, the absolute value we have here of the amplitude, as you can see here. When you do the post-processing, since you also do exercises, so when you have paraview, you also have the possibility there to switch between amplitude and phase, to switch to real and imaginary part, and then the imaginary as well as the real part can also have negative values. If you just plot the amplitude, it means it's the absolute value, and that just can be between 0 and some positive value. Okay, so let's have some investigation with two different computational grids. One here with very nice rectangular elements, and here also with triangular elements. And if you look and have a closer look here, these are very good shaped triangular elements. So the angles you have here between the different edges are almost the same, and that means it is a high quality triangular mesh. Now, if we look here at the number of unknowns, you will always have such a situation that will be then also in 3D when you use, instead of tetrahedra, hexahedra. With quadrilaterals or hexahedra, you will have less number of unknowns as you will have with triangles or dead elements, but it is not so much as you can see here, the difference. And what you see, we do an investigation. We now just have to do a space discretization because we do a harmonic analysis. Once we take 10 elements per wavelength, and here you see the finest grid is 40 elements per wavelength. Okay, let's have a look. What is the investigation we do? We look here along this line here, along this line, and just plot the acoustic pressure along this line. And this is here a first plot with the coarsest discretization, and the reference has been done with a very fine mesh, as you can see here, with lambda over 100. Okay, what you see here, you have really strong deviations for both meshes compared to the reference solution, which already decreases strongly, as you can see here, when you go from 10 elements per wavelength to 15 elements per wavelength. And please also consider that actually in acoustics we are always looking at dB scale. So this is a linear scale, as you can see here, and you know that actually what we are looking for is always in dB. Okay, if you go to 20 or even 30, you see then almost here no deviation. And what is also important to notice is that both meshes more or less come up to the same solution. So also the triangular mesh, which clearly has the not so good properties coming from the basis functions. You know, a triangular element has a linear basis function, a quadrilateral element has a bilinear basis function. But anyway, as you see, the difference is so small that we can neglect it here. Okay, and that is then in one plot. We just look at the relative error. So we compare everything to our reference solution. You see on this axis the discretization over the discretization length of the elements over lambda. And you see that we have almost a same behavior, how this error reduces according to the refinement. The relative amplitude error here in percent, you have to consider that this is an accumulated error because we add all the errors in all the finite element nodes up, and you know the finer we get, the smaller the elements are, the more elements we have, and therefore you have to look also that this is an accumulated error measure we have here. However, what is perhaps of great interest is that you should remember is at store is that the big difference if you do a HFEM means you make finer and finer meshes to get better approximate solution, and the other way is called PFEM for higher order finite element method. P then means the order of the finite element methods, and in order to have a fair comparison, we compare it, as you can see here, with the number of unknowns, because for the PFEM the mesh is always the same, but we go up with the order of the finite elements. So we have first order, second order, cubic order, and so on. And with HFEM, we keep the order of the finite elements, in this case, first order finite elements, and we refine the mesh. And as you can see here, you have an extreme reduction for the PFEM, it's the red curve. And then this just means due to the precision of your computer, you cannot really reduce the error more as shown here. And you see you have this reduction of the error when you have the standard HFEM approach. And since our solution is a smooth solution, here it makes more sense in order to get a more accurate solution to increase the order of the basis function, because you get, as we call it, exponential convergence, and you just get the algebraic convergence when you have HFEM, so you refine your mesh instead of increasing the order of the basis function. So that should be a very important result, just in order to remind you when you want to do simulations and you have the capabilities. Not all commercial or open source softwares have this property to also provide you with a PFEM approach. Okay. A very important property for all wave propagation, it's the same also for electromagnetic waves, and clearly here, as we discuss acoustic waves, is so-called open domain problems. You always want to restrict your computational domain just to such a domain where we are interested in computing the acoustic field, and we are not interested in make it larger and larger. But if you have free radiation, what to do at the limiting computational domain? Yeah, when you consider here, this is your computational domain, and let's make it very simple. You have here a excitation by a very small loudspeaker. Well, then you would have here such waves propagating outwards. Yeah, and when they impinge the boundary, as I make here now the boundary in red, then we don't know what to do there, because we should know the solution, but we don't know the solution. So we should have some approach that when these waves are impinging here to the boundary, that they are somehow absorbed and not reflected back into the computational domain, because then our model would not be what we want to simulate. So let's investigate this in 1D, because in 1D we have analytical solution. As you can see here, this wave is propagating to the right, so to increasing x values, and this should be now our limiting domain. And clearly what we want to have is that these waves can propagate through without reflections, and if some waves are coming from the right going to the left, they should be reflected here and not coming into our computational domain, so that we have a correct model which we solve with the finite element method. So what you can see here, this is the analytic solution for a 1D wave with wave number k. K is just the angular frequency, 2 pi f over c, the speed of sound. And as you can see here, what we have is a constant pressure within this propagation along x. That would be like our channel example we had. And you have then this exponential function with the argument, the complex number j, omega t minus kx. And this wave is propagating to the right, so to positive x direction, and that would be the solution if it is propagating to negative x direction. So now let's make an ansatz. You can also show this analytically, but that takes some time. So let's say we do the following ansatz. We do an ansatz in this sense that we have time derivative and space derivative. Perhaps you remember that was the thing I always emphasized very often, that we have this periodicity in space and time, and that is why we have a second space derivative and a second time derivative, and this is the balance within a wave equation. Now, and you have a scaling factor, and that's the speed of sound. Now, when you do such an approach and you set this to 0, it would mean that you can substitute a space derivative by a time derivative and just scale it with -1 over speed of sound. Why this is coming, I can show you, because the wave equation, I perhaps write it here, you know the wave equation is 1 over c squared, second time derivative minus second space derivative, we do it also in 1D, is equal to 0. And you can decompose the operator simply by now the following. I first multiply here that I get the same as here with c squared, and then I decompose it with dp, or I write it in a more elegant way. So you have an operator d dt plus c d dx. That should be the coordinate x. And multiply it by d dt minus c d dx. And this whole operator is operating on the acoustic pressure. And you know this is simply the formula we learned in school. A plus b multiplied by a minus b is a squared minus b squared. And so you see this is the factorization actually of the wave operator. And that is why we make this ansatz, and that makes clearly sense. And this is even optimal in 1D. So you cannot have any better idea as this what I just show you. So let's investigate it. As I have told you, we have a wave traveling in positive x direction which has this analytical expression. So when we now put this in to our ansatz, we should get out 0. And that is immediately the case, because when we do the time derivative, then it is this value. The inner derivative is just j omega. And if we do the space derivative, then the inner derivative is minus jk. And you see, if you add these two, then you clearly get out 0. On the other hand, when we assume a wave coming from right going to left, so in negative x direction, this we will see cannot enter, because when you again evaluate this ansatz, then what we get here is the following, that due to the fact that you have to look here at the exponent, it is here omega t plus kx, and that means that this time derivative plus the space derivative clearly is not equal to 0. Okay, so waves coming from left to right, in our case, going into positive x direction, they can pass. Any waves coming from right going to left, they cannot pass, they are reflected, so they cannot enter our computational domain, which in summary means this is a optimal boundary condition, and we just substitute our space derivative by the time derivative. Okay, now what to do in 3D? Well, in 3D, you have the derivative not to one spatial coordinate, you have a derivative to the normal vector. So our first approach, and that is why you call this absorbing boundary condition of first order, is, well, we also substitute the normal derivative by the time derivative scaled with minus 1 over c. The impact will be that just orthogonal impinging waves are optimal absorbed. That is exactly the property of plane waves, of one-dimensional waves going towards the boundary. But if you have any angle which is not orthogonal to your surface, you will have partial reflections. So how do we incorporate it into the weak form? Perhaps you remember, we do an integration by parts of the Laplace operator, multiplied by the test function. You know, our test function is b prime, which means we get out this integral here on the computational outer surface on our boundary, and there we now substitute, as you can see here, our normal derivative by this time derivative, and we should not forget this scaling factor minus 1 over c. Okay, which means at the end that in addition we get here some values for a so-called damping matrix. You know, we call a matrix a mass matrix because it's multiplied with second order time derivative, a damping with first order, and the stiffness matrix directly with the unknown. Which means at the end that we have here this formulation here, and we get here this additional matrix here, which is multiplied by the first order time derivative of the acoustic pressure, or it's the same if you use the acoustic potential formulation. And as you know, coming from here, we know that the entries are computed here like a typical so-called mass matrix, because a typical mass matrix, the entries are computed by the multiplication of the basis function, and you see this here. The main difference is this is just on the surface and not within the volume. We have to evaluate it, so we will have very less entries in this so-called damping matrix. Let's have a look how good this is working. If you look here at these two pictures, so the first row is, as you can see, we have this as a computational domain. We excite here with a point source, so we get nice waves propagating out. If you use homogeneous Neumann boundary conditions here, so you don't do a correct treatment, you see here the waves are first impinging, they get reflected, and you get a total distorted acoustic field, which is not what you want to get, or you want to model with your ansatz. And if you use here now the absorbing boundary condition we just discussed, you see that, well, the acoustic field looks quite nice, but it gets also somehow distorted. And that is because it is just optimal absorbed for waves impinging orthogonal, and that would be exactly just in this point, this point, this point, and this point. And then all other regions of the surface, we will have partial reflections. Let's have a look at this. So we have here the evaluation over time at point P1, which is in the corner, a very nasty position here, because there we are far away from our definition that for a good working of the absorbing boundary conditions, we need orthogonal impinging waves. As you can see here, this will be very bad. The best would be at P2, but still, as you can see here, also for P2, it's the green. So you nicely see how these waves comes and then starts to be absorbed, but well, it is also a little bit, as you can see here, distorted. And so actually what we again here excite is, as you can see, just with one period of a sine excitation. And P2, nicely you see also the time delay. It takes a longer time to arrive for the wave in the corner as here, which is clear because the distance is larger, and therefore also the amplitude is smaller, but you see you have here stronger distortion, so that is far away from what should it look like as shown here. Anyway, it is a method which is heavily used because it almost needs no additional computational effort, and it is also very simple to be implemented. Okay, so this was a summary in this sense for computational acoustics, and as you have seen, we have very nice rule of thumb how to do time and space discretization, which we not have for a lot of other partial differential equations. And we have also investigated the problem of re-radiation, which we can cope nicely with this absorbing boundary condition, not in the optimal sense, but at least in a good sense. And if you want to have a more accurate solution, you just have to make the computational domain larger and larger clearly, then this impact of the not idle absorbing boundary condition will be reduced. The optimal way how you can treat this would be the PML technique, which we call the perfectly matched layer, and it is very similar as we have it in electrical engineering. You know, perfectly matching impedance matching would be also here applied, and with these tricks, but that takes some time to explain. We will do it in the course in the summer semester. There we will also discuss this perfectly matched layer technique. As you can see, according to the name, it is the following. You have your propagation domain, and here it is the following, that you do an additional domain, which is the damping domain, but this just needs in thickness direction about 2 elements, 2 to 3 elements. So this is our so-called damping domain, where we try to damp out all the waves, and which are entering this damping domain. And the big challenge is that at the interface between propagation domain and damping domain, we have this so-called perfectly matching. And then this is the optimal way how you can do it. But it's heavily involved concerning theory, and also then when you have a good formulation, also concerning the implementation. Okay, so the last part, what remains is now just the extension, how to couple the acoustic domain with a structural mechanics domain, especially when you want to simulate a loudspeaker. You have a vibrating membrane which is excited by a voice coil. So by Lorentz forces, actually the membrane is vibrating, and this is then radiating acoustic waves in the ambient fluid. So we will look here at some practical examples, look at the transmission conditions. So at the interface, we need physical conditions, how the mechanical field couples with the acoustic field. We will then again look how we can incorporate these transmission interface conditions into the weak formulation, and then we just discretize the weak formulation and come up to the coupled system for mechanical acoustic computations. And this you can do for all analysis types you are interested. Clearly, static analysis makes no sense, but you can do a transient analysis, you can do a harmonic analysis, and sometimes also, which is of big importance, also to do eigenfrequency analysis. So in principle, we have two different scenarios. The one is where we have a strong coupling. A strong coupling means that the mechanical field has a strong impact on the acoustic field, but also the acoustic field has a strong impact on the mechanical field, so on the mechanical vibrations of the surface. What is shown here is an ultrasound array. The array here for the excitation, these yellow structures are piezoelectric structures. They are excited, and then the structure vibrates, and that means you excite waves which are propagating, for example, into your body. It is used for ultrasound imaging, or it is propagating into a material where you do non-destructive testing. And with the same array, because the piezoelectric effect can be used as an actuator as well as a sensor, then when the reflected waves are coming back, they impinge on the piezoelectric transducers. You have switched to the receiving mode, and you get induced voltage signals out of your charge amplifiers, and then can make out of these signals a picture. The second case, which is also quite often in practice, is that we have a weak coupling. And the weak coupling means mainly that the excitation of the waves has a strong impact on the acoustic field because they excite the waves, but the resulting acoustic field has a very small impact on the vibrations of your structure. You even can neglect it. If you look here at the power transformer, then you know power transformer also make a lot of noise. That is due to the vibration of the coils where Lorentz forces are acting, and it could be also due to magnetostrictive effects. And what you see here is the outer part of a transformer, the so-called tank, because the active part with the coils is inside such a tank which is filled by oil. And when the tank starts to vibrate, then you have radiated waves. However, the acoustic field being generated here will have almost no reaction back on the vibration. So we can do a separate computation. You first do the computation of the vibrating surface of the tank. Use then the surface displacements, or you even store velocities or accelerations, and use this as boundary condition for a second computation, which is a pure acoustic computation. Okay, so in general, it's clear we have here the mechanical PDE, we have the acoustic PDE, and we have a coupling interface. And the coupling interface is really as shown here. Therefore, we call this also a interface or surface coupled problem, because we have not both partial differential equation on the same computational domain. They are separated by the interface I have drawn to you, as shown here. And on this side, you do structural mechanics. On this side, you do computational acoustics. And along this interface, we will now look at the coupling conditions, which we will then incorporate into the weak formulation. Okay, so we have to specify the coupling conditions. We will then insert it into the weak formulation. And the very important thing is the normal vector. The standard way is that the normal vector, as shown here, is used as the normal vector of the solid, so of the structural mechanical domain. You know, the normal vector is always pointing out of the volume. So that means this will be the normal vector of the solid body, and I write this here and draw it. This will be the normal vector of your acoustic domain, because the acoustic domain is on this side. This is the volume of your acoustic domain, and then clearly the normal vector pointing out of this domain. So they have clearly somehow the same direction, but with a minus. And that we have to take into account, because when you do integration by parts, you then apply the Gauss or divergence integral theorem. You need to have a unique normal vector for both partial differential equations. So we once have the so-called kinematic coupling condition, which means we have a continuity of velocity and acceleration. And this is a very important thing. You see that the normal component of the vibrating mechanical structure on the surface has to meet the normal component of the particle velocity of your acoustic domain on the coupling surface. And as we know, we can substitute here also the particle velocity by minus the gradient of the acoustic scalar potential. So this is also an important thing which we will need when we do a coupling where the primary quantity in the acoustic field will be the scalar potential, the acoustic scalar potential. On the other hand, we can do a time derivative, and then the acceleration in normal direction of the vibrating surface has to meet the acceleration of the acoustic particles in normal direction. The second is the dynamic part. The dynamic continuity condition means the continuity of forces. Sigma is our stress vector, for example, Cauchy stress vector, kind of a 3x3 matrix. And when you take a dot product with the normal vector, then you get the stresses in normal direction, which is a vector, and that has to meet the acoustic pressure P scaled by the normal vector, and as the pressure is always acting into the body and not out of the body, it's very important that we don't forget to put here this minus. So you see that here we are coming from the acoustic side, here we are coming from the mechanical side. These are the coupling conditions, and now we just have to use this coupling condition and reformulate it with our primary quantities. And as you know, the primary quantities for us is the mechanical displacement, the acoustic pressure, or instead of the acoustic pressure, it could be also the acoustic scalar potential. I have always written it here with the A for acoustic, but in all the derivations we neglect it at the end because we know it is always the acoustic pressure we are discussing here within this topic. Okay, what else do we know? And that is important. We have the linearized momentum conservation. This is the linearized, or also sometimes called the acoustic momentum conservation. That was our, and you know, we also have the acoustic mass conservation, and we also know, which we get actual out of this equation here, is that the relation between the acoustic pressure and the acoustic scalar potential is given by this equation. Okay, now we have everything, and we just take this information and make now the coupling conditions for a pressure formulation as well as for a scalar potential formulation. Okay, let's start with the acoustic potential formulation, which means, what do we have? We have, as shown here, what we are exploring is this part here, because out of this linearized momentum equation for acoustics, we get the relation in this sense that the pressure can be expressed by the time derivative of the scalar potential with the mean density, and we have here clearly, since the curl, this is because the curl of the acoustic particle velocity is 0. We know we have a irrotational field, acoustic field, because we have no shear forces within the fluid, and so we can substitute the acoustic particle velocity by minus the gradient of our acoustic scalar potential. Okay, so the continuity of forces, which was our first coupling condition, now can be simply rewritten. We can express clearly the velocity by the time derivative of the displacement on the mechanical side, and on the acoustic side we substitute the acoustic particle velocity by minus the gradient of the acoustic scalar potential, and taking the normal, the dot product with the normal vector then means the space derivative with respect to the normal vector. Okay, now we have everything. Our coupling conditions is as follows. We know that this normal derivative of the scalar acoustic potential can be replaced by the time derivative of the acoustic, of the mechanical displacement, dot product with the normal vector. And on the other hand, we have the continuity of the forces, where we substitute, as shown here, the acoustic pressure by the time derivative of the scalar acoustic potential scaled with the density of the fluid medium. And so we see how the mechanical displacement couples into the acoustic PDE, and here we see how the scalar acoustic potential couples to the mechanical PDE, because you know perhaps I should also write it here. This was just, as we have shown before, our stress tensor dot product with the normal vector. And exactly this term and this term we have within the weak formulation when we do the integration by part, when we apply the integral theorem of Gauss, also called divergence theorem, and then you see how we can substitute these quantities and get then the coupled weak form of the mechanical acoustic problem. On the other hand, when you want to have described the acoustic field by the acoustic pressure formulation, which is very often used, then we also will have to do some reformulations to get there all our coupling conditions with the acoustic pressure. We have the first continuity of the velocities, and in this sense we also know that we have the relation between acoustic particle velocity and acoustic pressure. Now when we project this on the surface, meaning that we take a dot product here with the normal vector, then instead of the gradient of the pressure, it is the normal derivative. This is then, according to this equation here, the dot product with the normal vector, and due to the continuity with the vibrating surface velocity, which is du dt, we have then that our normal derivative of the acoustic pressure is now direct proportional to the acceleration, as you can see here, because it's the second time derivative. Okay, and the coupling conditions then are as follows, because the continuity and equivalence of the forces was already expressed by the acoustic pressure, as you perhaps remember, and that we have got from here. And so we see how the mechanical displacement couples to the acoustic PDE expressed by the acoustic pressure PA. And you see this is over the acceleration. And this is also important to note that this is actually the physics, how pressure in the ambient fluid is generated, that the acceleration of the surface vibration is the important quantity and not the velocity. So important is the acceleration, and that we see here nicely. And this shows us how we can substitute the normal stresses by the acoustic pressure, and then this will show us how the acoustic pressure couples to the mechanical PDE. That we will now look and investigate. We just look to derive the weak formulations. We use here u prime and p prime as the test functions, and you can look up at the part of the mechanical computational mechanics as well as computational acoustics. Then, as you know, the following, we have here a first term within the weak form of the mechanical system, where we have exactly here this part, which we will be able to substitute. And we have here this part within the acoustic weak formulation, where we are now able to substitute here the gradient of the acoustic pressure in normal direction. We just have to be careful, because once we have the normal vector ns and once na, and you know that our notation is that the overall normal vector will be taken as the normal vector of the solid, and therefore this is equal to minus the normal vector of the acoustic domain, which is also summarized here. Okay, that means now the following, that we look now for the coupled weak formulation, which means in this formulation we will substitute for this and this integral here, and for sake of brevity we use homogeneous Neumann boundary condition on the outer computational domain. It could be also a absorbing boundary condition for the fluid domain or whatever, but let's make it simple. We want to concentrate on the interface where the acoustic field is coupling with the structural mechanical field. Okay, so what we are doing in the weak formulation, we have obtained in the not coupled weak formulation, the pure weak formulation of computational mechanics and computational acoustics, we will substitute the mechanical stress tensor in normal direction by the acoustic pressure, and we will substitute here the normal derivative of the acoustic pressure by the acceleration in normal direction scaled by the mean density of the fluid, which gives us now this coupled weak formulation for systems where you model the coupling between structural mechanics and acoustics. And as you can see here, we get an additional term on the coupling interface in the mechanical equation. And you see how the acoustic pressure couples into the mechanical weak formulation, and on the weak formulation for the acoustic field we get this term here, and you see how the acceleration second time derivative of the displacement couples into the weak formulation of the acoustic system. And the same we now can do also for a formulation where we describe the acoustic field by the scalar acoustic potential. We have discussed how to substitute these terms, which was this relation here between the mechanical displacement, so the velocity in normal direction of the structural body on the surface, with the normal derivative of the scalar potential, and here the time derivative of the scalar potential with the mechanical stress tensor in normal direction. And that gives us exactly this coupled weak formulation, where we have here now this term here. And as you can see, we have here a first order time derivative, and in the acoustic weak formulation we see how the mechanical velocity, the time derivative of the mechanical displacement, comes in, and you see here also a time derivative. And that means when the only difference between these two is that we have here this mean density. So actually, and don't forget that here is a plus. So when you multiply this here by minus the mean density of the fluid, then you will get a symmetric weak formulation, and therefore also at the end a symmetric system matrix, which is not the case when we use a acoustic pressure formulation. But that is the main advantage you have compared to the acoustic pressure formulation. Okay, so as we already have discussed, the discretization for computational acoustic as well as computational mechanics are standard nodal finite elements. When we apply this space discretization, we get a system of coupled ordinary differential equation of second order, as we can see here. And important to notice is that once we get here a coupling matrix, which shows us how the mechanical acceleration, this is this double dot this double time derivative acceleration couples into the acoustic equation. And once we get here the coupling within the overall stiffness matrix, where we see how the acoustic pressure unknowns are coupling into the mechanical system. If we now combine the unknowns at all the nodes for the mechanical displacement and acoustic pressure, we can also write it down as a standard form with a overall mass matrix multiplied by x double dot plus a stiffness matrix K multiplied by x is equal to any right-hand side. And we have a system matrix which become here unsymmetric, which is clear when we look at this overall mass matrix and when we have a look at the overall stiffness matrix. On the other hand, when we use here this acoustic scalar potential and we multiply the wave equation by this part here, and to be very correct, that should be minus actually, then we get here an overall system where the coupling, as you can see here, is within a kind of a damping matrix, but it is not really a damping matrix because from the physical point of view, it is not really damping the waves, but we get the coupling within the damping matrix, which is multiplied by the first order derivatives of our unknowns with respect to time. And we come up to a symmetric then system matrix, as we can see here. Okay, and this is important to note, which I already have told you. It is a pure diagonal matrix, no diagonal entries. In this sense, this matrix, as you can see here, the diagonals are zeros, and so it has not the character, the physical character of damping. Okay, so you see, you can use scalar potential or pressure formulation. It is not a big difference, and you get then this coupled system of equation. Yeah, and clearly you can then do a harmonic analysis where we do just a Fourier transform of this semi-discrete Galerkin formulation as shown here. You can do a transient analysis. For the transient analysis, we just use a Newmark time-stepping scheme, as we have discussed within computational mechanics as well as computational acoustics. They are both partial differential equations with second-order time derivatives, and clearly we can also do an eigenvalue analysis to find the coupling modes of such a structure. For example, when we look here of the eigenmodes you have of, let's say, a tank, which is once filled by air, once filled by oil, you will see that there will be quite big differences in the eigenmodes you can compute, because air has a very low density, about 1, and oil about 1,200. Okay, so the big difference, if you use pressure formulation, you get the unsymmetric matrix, which means you need special storage formats in storing these matrices, and sometimes it also depends clearly. The eigenvalue solvers are more involved. It's more difficult to solve the eigenvalue problem for a pressure formulation because you have unsymmetric matrices as for a acoustic scalar potential formulation. Yeah, and the special topic, which we will also discuss in summer semester, is the capability of so-called non-conforming grid techniques. As you especially can see here, we know that we have here structures which are the structures of a loudspeaker, and when they are vibrating, they generate the acoustic waves, and we also want to compute the generated acoustic field. We have here the interface as shown here. Perhaps I make it below the interface between the membrane and here the ambient fluid. And well, it's a difference if you do such a mesh as you look here, where you have a conforming mesh, which means that the discretization you have within the solid you have to keep within the fluid and then perhaps try to coarsen your mesh there, or you have the capabilities of so-called non-conforming grids, where you immediately, as you can see here, you immediately can jump with the grid size. Now, to give you the motivation, this has a thickness of about 2 millimeters, 1 to 2 millimeters. Yeah, and then you have to discretize this membrane. On the other hand, don't forget, if you are interested here, we have a wavelength which is 340 over the frequency. And let's say we are interested at the radiation at 1 kilohertz. Then you see it is 0.34 meter. So you see this big discrepancy you have, and therefore it is highly beneficial when you can have such methods as non-conforming grid techniques. Actually, what you do is then that at the interface you have to fulfill the interface conditions on grids which are not matching, and you somehow have their mathematical algorithms which are called mortar methods. Mortar is coming from Greek and means just gluing together. Okay, this is also a very special technique. I think in 10 or 20 years you will have it in all the commercial programs, because it also helps you to reduce the effort concerning preprocessing, because you can individually mesh each substructure and then just glue all these substructures by a numerical algorithm together and get the same solution as you would use conforming grids. Sometimes you get even better solution because you can do the discretization within the fluid domain totally without considering the structural domain. The only thing what you need by these techniques is that along the common surface you need also the surface grid coming from the fluid and coming from the structure. That is all what you need by these methods. Okay, so this was the last coupled field I wanted to discuss with you and to present to you within this course here. And as you know, next week you have a final task which is exactly concerning this coupling between mechanics and acoustics. So next week we will have the discussion about this final task. And we can also fix next week then when we will have the exams, you know, the oral exams. Most of you, for most of you, it will be almost no additional work because you have done all the homework, and we will just discuss about your homework. And there also, perhaps I will focus to those things which were not fully clear to me in your homework, or which were not fully correct, as we discussed all the tasks up to now and we will also discuss the last task for coupling mechanics with acoustics next week. Okay, so now I have told you a lot of things. Do you have any questions? Also perhaps concerning the exam or other things? Okay. If this is not the case, as I've told you, we will have a last lecture next week, and there we can then try to answer all your questions concerning the exam. And I also like to fix somehow the exam period so that you can do it how it is appropriate for you. Okay, so if there are no further questions, then thanks for being online and see you next week.